troubleshoot would happen. Actually, the system administrators or the network administrators, they have to actually start by actually the troubleshooting versus the network vulnerabilities. As per the concern of our full chapter, which is the chapter number 5 here, the network defenses, all of the activities we do here are considered to be solutions to the troubleshooting. Yet mainly, we have to recognize what are the entry points where the data flows actually they are going in and out. And there we start the troubleshooting, whether we are talking about physical media or we are talking about a logical setup. From there only the troubleshoot start. Troubleshoot means actually to check up the filtering activity, is it set or not? In the sense of, is it controlled to allow the flow to pass or not? In this sense, because in the network we do not see humans passing, we see only flow passing, frames and packets. So those frames and those packets, are they filtered or not? So this is the troubleshooting in real scenario mainly. How it happens actually by just setting filters in different locations to tackle every single weakness, which is a vulnerability, a kind of a vulnerability, and from there the remedial starts. So briefly, and let's get started. We said that the network defenses starts with the physical architecture of the digital, let's say, of the computer network in question. Physical architecture in the sense of we are going to tackle the segregation of the network elements into parts. In a given network, the service provider would segregate the regions within his network into parts: part number 1, part number 2, part number n, and so on. Department number 1, department number 2, department number n, and so on. And thus the technology has to be implemented and has to be deployed to guarantee this behavior, this physical approach. The first technology to actually, as per the objectives of this chapter, we are not the technology we are going to talk about is the context of the scenarios, how we are going to match the inner world with the external world. What is the inner world and what is the external world? We talk about when we say actually we are going to segregate a network into parts. It means we have part number 1, trunk number 1. Part number 2, which is the trunk number 2, and so on. Trunk number 3, trunk number 4, trunk number n in the same network maybe. And we have a full local network in addition to the external, the public network, for example, the internet. So how we are going to make parts communicate and how we are going to make networks communicate, this is the scenario actually of this nothing here as per an example. It's not the unique technology we're going to adopt to troubleshoot and to set a network defense. The network address translation, as per the literally speaking here, the title. It is a scenario via which we are going to change the addresses into a language that the communicated party will not understand which destination is. We are hiding something from the external member. A is sent to B, so A's address has to be actually obscure somehow. So the NAT will do something like that. So it's a network defense, something like that. This is one of the network defenses via which we are able to hide the internal world from the external world, and so on. We'll go step by step. This is actually the third approach, which is as per an objective of this chapter also, which is to talk about the network devices. Inside the computer network, we do not have only terminals. We do not have only peripherals to use to communicate. But the network devices, they are also essential members from within a computer network. And they do represent the question of defense. Because once one of them is vulnerable, it might cause a damage to the full network. remember that the equipment from within a network actually they belong to commentary just came in. They are belonging to different layers from the OSI model, since we can see a switch from the layer number 3, a router from the layer number 3, and they are smart enough to have a list of control functions. Once one of them is actually compromised, so those list of functions, they are also compromised, and thus all the beneficial parties from those functionalities will be actually under attack. So thus we talk about devices from within a network security. Devices security. Great. From the actually first perspective, actually, to secure a network, we have to segregate, as we were talking, the network components into trunks or into departments, into small parts for an easy control. But this scenario, if it does not happen, and security, let's say system admins or network admins, they try to go for updating all the, let's say, operating systems running within the network, it is not the best behavior to do. Why? Because if the network where updates has been happened is weak enough to support all of those patches, the updates means vulnerabilities will persist. Means those patches, they will not be a remedial for the vulnerabilities. Why? Because we know so many actually scenarios and techniques that lead foreigners to access the network due to the weak configuration of the network. So the first scenario is to harden the architecture, the design of the network. Then we talk about the operating systems improved patches, which are the security updates. Talking about physical and designing the network into small trunks, let's say, here is a physical segregation of the elements of the network. Here we talk about subnetting. And the scenario, let me pass immediately to the graph. We explain it again. We can see actually here, see if you can, you see where I'm pointing exactly. This IP address 196.98.34.0. Here is one. The other part 196.98.33.15.33.44. Here 0, here 15. This is the number here. This is the last one, is the number where the computer is identified. Also here, this is the number where the computer would be identified. Also, it's somehow it's the one to identify the computer. All the others, all the other numbers, they are represent, actually they are discussing the network part. If we consider that this part will identify the network. 196 means we are talking about a class B network. 33, this is the trunk number 1. 34, this is the trunk number 2. 34 again, 33, 33, 34, 34, 34. So we are having two groups. This group here is subnet 1, and here is a subnet 2. The network is 196.98. The full network. The full network is identified with the network part 196.93. But we have two trunks. Physically here, actually, we can see that there is a wire connecting all, yet logically they cannot communicate. In the sense of this A here, for example, this computer, if it's considered to be A to send B message, then have to be respected the channel via which this computer will succeed in sending and communicating with this this computer B. Why? Because they do not belong to the same group. They do not belong to the same group. So this way, physically we are segregating the devices, the computers, the network, let's say components or elements, members, in two groups. So this is the first security we have to talk about, the subnetting. So here, subnet 1, subnet 2. Whatever. We talk about physical segregation. What is subnetting? Subnetting, at the end of the day, it's the segregation of the network components into departments or groups for a needs of control, for the purpose of a needs of control. We discussed this actually list of terminologies, but very briefly. Decreased network traffic, and the sense of, if we come back to the this graph where we see actually the subnets. This A cannot communicate with B. What does it mean? It means there will be no traffic from here, from this router to this computer. So the network traffic is going to be decreased. It is trivial. So subnetting leads to a decreased network traffic. The answer is true. Network traffic means the communicated data within the network media. Yes, there will be a decrease in the network traffic. Flexibility. Can we just add extra devices? Can we change the number of the devices within a trunk or within a subnet? Answer is yes. True. So the flexibility, we mean by that, are we able to increment or decrement the number of devices from within a subnet? How many devices in this subnet, for example? We have one router and one computer only. Can we add other devices? Absolutely we can. So we have there have to be a calculation to happen. And then later on, physically we can do that. Physically we can add more. So the flexibility, and not only that, if you talk about, for example, this full here network, if can we omit this server, if this one is a one subnet, can we omit this server from this subnet? Yeah, absolutely yes, we can omit. We can send him out. So flexibility is by incrementing or decrementing the number of members from within a subnet. Improve the troubleshooting, and that was the question at the beginning of this class. If something happened, an issue happened, or malicious, let's say, request is coming to this server, and the malicious request is identified with the header who is sending that. If we recognize the network at trunk, so it's an easy way to localize the network, the area. It's much more easier to localize from where the request has come. Or in plural, from where requests have come. So it would actually enhance the troubleshooting. It would actually make the troubleshooting more fruitful, more efficient. Troubleshooting means checking the issues and trying to solve. Not only that, another advantage, and this is a terminology you have to recognize due to the subnetting, which is the improved utilization of the IP addresses. What does it mean? It means actually when we identify a device, with a network, and we say that this one would belong to the subnet number one, okay, just give him an IP address. No, it's not like that. It's not like that. Subnetting means we are going, actually, at the beginning I told you, see, physically, there is a one wire connecting everybody. Physically, they are all connected to the same network. Yeah, logically, they are not able to see each other. Why? Because this is group number one, see the number here, 33. And this is another group, 34. And again, here, 34. But here we are, see, there is a calculation also to use even the number 4. They belong to different groups. They cannot communicate to each other logically. Logic means if this one sends to computer B, what is the computer B? It's in another network. So there is a scenario to allow him and to make his message succeed and reach this destination. Here we talk about improved improved utilization of addresses. in the sense of the range we are going to give here, it would be actually, for example, set to acquire only 10 addresses or 10 devices. Okay, we give a range of 10 devices only. Later on, we'll be able to troubleshoot easily, and we'll be able to add 10 devices or minimize. We can use these 10, 10 addresses as per the need or as per the request. So the improvement here is in the sense of you not be wasting IP address or allocating IP addresses where you do not utilize them or they are not being utilized. Just allocated for free. No, no. Impacts like so actually would be actually remarkably noticed with big networks, but with networks with 5 and 10 computers, it's not something to notice. But the improvement of the utilization of the addresses would be clearly not noticed when networks are big enough to be exhausted counting the devices and configuring devices. Okay, minimal impact on external routers. This is a router and this is a router. Okay, this subnet here would be actually running its content locally here from the router and in. There will be no request going out. So this router will not be impacted with any request from this subnet, and the vice versa. This router here, this one, would not be impacted with any device or any request coming from this subnet. So there will be a minimal impact on the external router. This is an external router to this subnet, and this is an external router to this subnet. By just having a physical site look to the computers, how they are set physically. You enter to the room and you enter to the network and you see the computers, how they are put. You'll have a first reflection how the subnet is, or the group of subnets are set, are being adopted. So the physical input of computers, the physical input, the physical segregation, the physical display, or let's say positioning of the computers will reflect the subnet, the view, how the subnets are, or what are the subnets. This is actually sort of a summary to all what we were discussing. Okay, we were talking about the subnetting and we said that it is a physical segregation, while we saw a graph like this one, which all the devices, they are connected physically using the same one wire, but logically we said that they are segregated using the addresses, different addresses. We were able to eliminate groups from communicating to each other while they are physically connected. So this is the context of the subnetting. Subnetting is not the unique scenario via which we control physically the access to resources. Here we talk about the network. The scenario of the virtualization is another approach. Physically, we segregate the communication from being exposed. What does it mean? We want only those computers, for example, let me pass to the next graph. Only we want those computers to be communicated to each other. None can communicate with them. For example, those 3 computers here. Can we do that? Absolutely we can. They are connected with all. Absolutely. Yes, and even if they are using a simple hub or just simple wire, there is no control. But we can, logically we can configure those computers to communicate to each other only. Here we talk about virtualization of the communication channel. What does it mean? It means we will generate a path, logically speaking, to lead this computer to communicate with this computer and this computer. That's it. Full stop. They are physically using the same wire where the signal can pass to all the devices. But logically, we will eliminate the external parties from seeing what has been happened in between those devices. So we are virtualizing the path, the circuit that interconnects those devices here. The unique concern here that we have to recognize is that those network devices, what are they? To help us achieving this virtualization, no more, no less. So are we equipped with devices that they do support the virtualization or not? No more, no less. Why? Because configuration here of virtualization is not to be done peer-to-peer. It's not going to be happening device to device. It's going to be happening within, and somehow actually you have to understand it this way, through a network peripheral, through a network media. And you can see it here. I was saying that we need to virtualize the communication between those devices. So how to do? What is the path? This is the path. 1, 2. It is passing through what? Through a local switch, workgroup switch. And this workgroup switch is connected to a core switch. What does the core switch? It interconnects all the local networks, the workgroups, which is exposing everything. Okay, I'm going to change the pointing now. See those circles here. Computer number 1, circle 2, computer number 2, circle 3, computer number 3, circle 4, computer number 4. They are belonging to different floors and to different physical departments. Ground floor, first floor, second floor. They are different floors in a very big building. And we need this computer and this computer and this computer and this computer. Only those computers to communicate to each other. What is the solution? Subnet? We cannot. We cannot do subnet here. Why? Because they are connected to different switches. Switch number 1, switch number 2, switch number 3. And those 3 switches, they are connected to a core switch. We cannot create subnet between those devices here. No. This can be subnet. And this is another subnet. And this is another subnet. Physically, we can say that. But logically, we cannot generate subnet between this device and those devices. They cannot create one subnet. No. Because they are physically very far. But we can create a virtual LAN, a virtual path, a virtual network made up of those 4 devices while they are physically segregated. Yes, we can do that. So at the end of the day, virtualization here, virtual LAN, VLAN, it's a scenario via which we see specific and dedicated computers generating one group to communicate to each other only. The segregation here is set actually, or is done logically. We are speaking in a logical way. It means we are not going to give a specific wire to connect them all. No. They will use the public one. But logically, they are using a different communication channel, which is dedicated to them only, which is the virtual one here, virtual LAN, virtual local area network. Why virtual? Because it cannot be seen by others. And it is not meant to be seen by others. It is dedicated to them only. Great. So this is exactly what we were explaining. Okay. So here actually we keep going on. The one question that comes to mind here actually, can we generate from a subnet, can we generate a virtual LAN? Means, is it possible to from a subnet we generate a VLAN also? From this is subnet 1 we said, this is subnet 2, and this is subnet 3. Is it possible to generate a VLAN 1, VLAN 2, VLAN 3? Answer is true, yes, we can. The vice versa, no. The vice versa, no. What is the vice versa? We have a VLAN. Can we, from every VLAN, create a subnet? No. Because see this example here of VLAN. The VLAN here is made up of this computer and this and this and this. Can we generate a subnet made up of this computer, this computer, this computer, and this computer? No, we cannot. So the vice versa is not valid. But from a subnet, can we generate a VLAN? Yes, the answer is yes. Any questions at this level, please? Any questions so far? Okay. So I believe everything is clear. So we continue in the context of the network defenses, and we talk about another service to be delivered over the networks, over the computer networks, which is the voice over IP. Computer networks, they are used also for communicating audio and visual contents. Like I'm doing right now, I'm explaining you this slide in a verbal way. I'm speaking and you're listening, and I'm asking and you're answering, and so on. We are interacting. So it's a voice over IP here. So the scenario here, it's based on the serves. Based on the serves, we set up a security approach. What does it mean? Means okay, how to secure what I'm just explaining to you now, or what we are discussing literally here, this slide and this topic, and we are interacting by questions and answers. So how we need and how we can secure this audio visual, let's say, communication. From the scenarios here is to refer to the convergence. In the sense of, we can give such services, yes, still, and we can allow the same services to happen also, whatever the security vulnerability or issue to be raised, yet we can unify the path via which such services can pass through. Convergence. So by using single IP network, IP actually dedicated to such service, here actually the segregation is based on the service, not based on the number, not based on the physical positioning, or let's say localization of the devices, no, but based on the service type, we set the security. And the security we talk about here is the convergence. We make the service run through a specific network or specific path to be allowed, otherwise to be blocked. So convergence. To converge, are you using the voice over IP service? Okay, you have to pass through this network. You have to pass through this firewall. You have to pass through this path or circuit. Convergence. One of the consideration and is one of the very famous, I think, is convergence, in the sense of, because if you want to secure what is happening in an audiovisual format, it is not easy to do if you're using a very public and wide network. Why? Because the thing is broad enough to impose complexity. But while when we use a dedicated path or dedicated network, to provide a service, so we can control it much more easier compared to the broad network. What are advantages? So when we give one unique network to such service, we are saving costs, absolutely, because to give a voice over IP service, it needs specific peripherals, specific network devices. When we use only one network dedicated to the service, so we are saving costs. In addition to that, configuration will be done only one time, once, only to the single network setup. The management will be set there only. It will not be done again and again and again to all networks, because we have only one dedicated network given the same service, which is the voice over IP. In addition to that, applications actually to be, let's say, from different perspectives here, from different perspectives. We can talk about the utilization, or we can talk about the implementation, all the tools to be utilized here for this dedicated purpose. They are to be unified in this sense. We will not see different applications for different candidates. No, we are using the same applications and the same resources because we are using the same network, same framework. All is compatible in this sense. The same way, since we are using the same network, so we are using a dedicated infrastructure to all, to everybody. Policies and politics to make the service run, they are actually minimal, in the sense of all the policies, they are only reduced to control one single network, not more. So reduced regulatory requirements. And this way, everything is controlled, and based on that, issues will be actually reduced and productivity will be increased. Any questions, please, at this level? If you say yes, please.